Welcome to part 2 of our lecture on exception handling in C#. In the first part, we covered the foundational concepts, how exceptions work, the try-catch finally structure, and how to prevent program crashes. In this segment, we shift to more advanced and professional features, how to create your own custom exceptions, how exceptions propagate, and how to apply techniques like exception chaining, resource cleanup, and parallel error handling. These tools are critical when developing large-scale, maintainable software. We begin with a practical debugging trick using x.toString to print the full exception details. This not only shows the message but also the stack trace, which is critical for identifying where the error occurred. This technique is helpful during development and debugging to get the full context of an error. In this example, a method called getResults might throw a floating PID division exception. We try calling it. If that exception is thrown, we catch it and display the custom message. If anything else goes wrong, a general catch block provides a fallback. This illustrates how you can target specific problems while also being prepared for unexpected errors. Sometimes the built-in exceptions aren't descriptive enough. That's where custom exceptions come in. They allow you to define domain-specific errors with meaningful names, like negative balance exception, making your code self-documenting and easier to maintain. Here's how you define a custom exception. Inherit from exception. Use the base constructor to pass a default message. In this case, negative balance exception carries the message, bank balance cannot be negative. This allows your logic to enforce business rules clearly and cleanly. In this example, the balance property checks whether the new value is negative. If it is, it throws our custom exception. This is a textbook case of defensive programming. Don't let invalid data sneak into your object's state. Now we use a try-catch block to catch the exception if it happens. We attempt to set the balance to 500 that violates our rule, and the negative balance exception is thrown. The catch block prints a user-friendly error message. This way, we enforce logic while keeping the program responsive and safe. It's good practice to provide multiple constructors for your custom exceptions, one with no arguments, one with a message and an inner exception. This gives flexibility when throwing errors, especially when wrapping lower-level exceptions. Here's how to use custom exceptions responsibly. Use them only when necessary. Don't overuse them. Always inherit from exception, not application exception. Provide clear messages, implement multiple constructors for flexibility, and make sure to log and document them. This is a custom exception for a specific condition, very small divisors in floating point division. It's a great example of naming your exception after what it checks for, making the code easier to understand. The method getResults throws the floating PID division exception when value 2 is nearly 0. This avoids a risky divide by near 0 situation, which could cause unstable results. Instead of failing silently, we now have a controlled, informative failure. Floating point values are imprecise due to how they're stored in memory, so instead of checking if value 2 is 0, we check if it's smaller than a very small number, like 0.01. This is a key concept in numerical computing. Here we see exception filtering in action. First we try to call getResults. If it throws floating PID division exception, we catch it and handle accordingly. Any other issue is caught by the fallback catch block. This layering makes our error handling precise but comprehensive. You can throw exceptions manually using the throw keyword. The moment it's thrown, control passes to the first matching catch block in the call stack. This lets you defer error handling to the layer that knows how to deal with it best. Exceptions move up the call stack until a matching catch block is found. If none exists, the program crashes. That's why we must always think about where to handle exceptions, not just how. Advanced exception handling is crucial for writing robust, maintainable code. It helps manage complex errors, ensures proper resource cleanup, and improves debugging by preserving detailed error context. It also supports custom logic and exception propagation, giving you full control over how your application reacts to failure. Finally is your safety net. It always runs, whether an exception was thrown or not. Use it for cleanup logic, closing files, database connections, or releasing locks. In this example, we open a file inside a try block. If the file can't be read, we catch an I/O exception. But either way, the finally block closes the files. This ensures no matter what happens, we don't leave resources hanging. This is a more advanced feature, exception filters. The when clause lets you filter based on conditions. For example, only handle the exception if the message contains a certain word. This keeps your catch blocks focused and efficient. When catching an exception, you can wrap it inside a new one using inner exception. This is useful when you want to add context but not lose the original cause. This pattern improves logging, debugging, and error transparency. In parallel or async code, multiple exceptions may occur. These are wrapped in an aggregate exception. The inner exceptions property lets you iterate through each one individually. Always remember to unwrap and inspect these exceptions carefully. Let's summarize some best practices. Always release resources using finally or using. Use exception filters for clarity. Use inner exceptions to preserve history. Handle aggregate exception properly in async code. Never swallow exceptions silently. Always log or rethrow them. Additional tips for resource handling. Release resources as soon as they're no longer needed. Use using blocks to simplify cleanup. Avoid keeping references to objects that are done being used. Resource management is about writing efficient and memory-safe applications. Every exception has key properties: message, human readable description, stack trace, sequence of method calls. Inner exception, the original exception if it was wrapped. These properties are your best tools when troubleshooting bugs. You can catch exceptions using their base class. For example, catch exception X will catch any exception. This is useful for logging or fallback behavior, but it's best paired with specific catches first. How do you know what exceptions a method might throw? Check the official documentation. For example, int. Parse might throw format exception or overflow exception. Planning your catch logic around this avoids surprises. Let's end with a quick recap of exception object properties. Use message for display, stack trace for debugging, and inner exception for wrapping behavior. Understanding these helps you write better logging and error reports. This concludes part 2 of our lecture on exception handling in C#. We explored how to define and use custom exceptions, manage advanced error flows, and apply patterns like filters, inner exceptions, and resource cleanup. You now have the tools to not only detect and handle problems, but to design your code to recover gracefully, log intelligently, and maintain reliability under stress. In the next part, we'll look at how exceptions behave when uncaught and how to set up global error handlers in real-world applications.